Okay guys, welcome back to a new IMONST video. So in this video, we'll be talking about Junior IMONST 2 2020 problem 3. So let's look at the problem. Given integers a and b such that a squared and b squared is divisible by 11. So we need to prove that a and b are both divisible by 11, meaning that both of them are multiples of 11. Okay, so divisible by, you can just equate that to multiples of 11. Okay, now here's a few things I need to tell you. In this, I'll be using mod. So if you guys do not know, I'll give you a brief overview. So take for example, we have a certain number. So say like 17. So 17 divided by 5, this is a very easy divisibility problem, right? So 17 divided by 5, we will get 3, and then minus 15, we have 2, right? But then again, we can rearrange the equation to become something like this. 17 equals to 3 times 5 plus 2. So 5 is our divisor and then 2 is our quotient, okay? Divisor, quotient, okay? So since 17 is a certain multiple of 5 and then we add 2. So we could say that in mod 5, this is the general notation, 17 is congruent to 2. Something like this. Why is this so? Because we could say, oh, we have some 5k, so multiples of 5, multiple of 5 plus 1, 5k plus 2, 5k plus 3, and then 5k plus 4. We don't need 5k plus 5, but because it's already a multiple of 5, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Give me a moment, let's move down a bit. 14, and then we will have 15, 16, 17. As you can see, 2 and 17 are at the same column here, so that's why they are called congruent, okay? Sorry for the jump cut, let me continue. So now, I would like to introduce a few facts about mod, okay? So the basis, the gist, I'm sure you guys have kind of get it already, so a few facts. So say in mod n, so divisibility by some n, okay? So any integer a, we're just talking about integers, we're not talking about any decimals here. A would be congruent to some multiple of n plus a. The multiple could be positive, it could be negative, okay, and such. Now, this second fact is the one that we're going to be having more discussions about today. So we will have a square is congruent to, okay, another bn plus minus a square, okay, mod n. Now, why is this so? Because we can take out this bn plus minus a squared. I can make it become, okay, b squared n squared, and then plus minus 2 abn plus a squared. So as you can see here, both of these are multiples of n, right? So we can remove them because in mod n, they're just equal to 0. Then we are left with two sides a squared. So hence this fact. Now, this thing is given a special name, is assigned a special name. We called it the quadratic residue. Now, quadratic residues play, I would say, quite an important role in this part. Of course, you don't need this to solve it, but if you know about quadratic residue, it would be a very beneficial thing, because quadratic residues are basically what are the remainders that a certain square would give if they are divided by another certain number. So in this case, we are talking about 11, right? Okay, so mod 11. In mod 11, if we say a square, if we say any integer a square, what are the remainders that they will give when we have mod 11? Of course, these numbers will generally be smaller than 11, so between 0 and 11, okay? So let's take a look. Now, let's list out the quadratic residues of 11. So, mod 11, okay? Mod 11, I'll just use this to represent mod 11, okay? These two apostrophes. So 1 squared is congruent to, obviously, 1, since it's smaller than 11. 2 squared to 4, 3 squared to 9, congruent to 9. And then for 4 squared, since it's 16, you can minus 11 and then we'll get 5. So 4 squared is congruent to 5 mod 11. 5 squared is 25, we can minus 22 and get 3. So 5 squared is congruent to 3 mod 11. Now, for 6 squared, since we've mentioned before, right, the quadratic residue thing. So let's go back up a little bit and look at the second fact, okay? So 6 squared is equal to 11 minus 5 squared, right? So as you can see here, it fulfills this condition. So we would have 6 squared is congruent to 5 squared. So we would have 3 mod 11. So we can go back and just see, oh, 7 squared, 8 squared, 9 squared, 10 squared. You can just do something like this. So since 8 and 3 add up to 11 and stuff. Okay, so all of these. And then finally, we will have 11 squared. Since 11 itself is a multiple of 11, so 11 squared is congruent to 0 mod 11. Okay, so the quadratic residues of 11, as we can see here, are 1, 4, 9, 5, 3, 0. And then if we write them in ascending order, it'll be 0, 1, 3, 4, 5, 9. Only these 6. Okay. So for any 11a plus b squared, so when you are asking about mod 11, they will only produce these results. Okay. So there are no 2s, there are no 7s, there are no 10s. Okay. Something like this. Now, so using this fact, what can we do? Okay. If we want to say a squared plus b squared is divisible by 11, right? So let's see. Now, using this, we can just say a squared plus b squared is congruent to 0 mod 11, right? Now, let's look at these, okay? Do we find any two of these numbers which add up to become to 11? So at a first glance, you could try this. So maybe after a minute or two, after you've tried all the combinations, you would find that no two numbers except for 0 and 0 can add up to 11, right? So since there's only 0 plus 0 can be 0, or say multiple of 11. So of course, a squared and b squared are both multiples of 11. So are both multiples of 11. Okay, and from this we're just done. Of course, this is the idea. So in this solution, I'll be using our quadratic residues. Then if you know quadratic residues, even before entering BMO, this is quite an achievement actually. So let's write out our solution. Now, font 20, then we'll start writing our solution. Our solution will be very short, sweet, and concise because we already know how to use quadratic residues. Okay, so the quadratic residues, you do not need to tell them what quadratic residues are. The markers will automatically know. The quadratic residues of 11 are 0, 1, 3, 4, 5, 9 mod 11. Okay, so quadratic residues being a squared and then congruent to what number mod 11, right? Since out of these 6 quadratic residues, no pair other than 0, 0 plus 0 add up to become a multiple of 11. Note that 0 is still a multiple of 11 because 0 times 11 equals 0. 0 is a multiple of everything. We can say that a square and b squared, okay, are congruent to 0 mod 11, and hence both a squared and b squared are multiples of 11. Now, for the quadratic residues, kind of changed my mind. It might be not enough, okay? So we need to demonstrate to them what the quadratic residues are, okay? So we just write right here. Move down a little bit. Now, the quadratic residues of 11 are 0. It is shown as follows, okay? It is shown as follows. Okay, so any 11a plus minus 1 squared would be congruent to 1 mod 11. Then any 11a plus minus 2, this thing squared, will give us congruent to 4 mod 11. Okay, and then the last one, 11a plus minus 3, this whole thing squared would give us 9 mod 11. It's just repeating stuff, so let me copy and paste my things. Now, just copy, right? And then we paste it. So sorry guys, this is taking so much time even though this is just one question. Okay, and then we have the last row. So this is 4, this is 5, then we do not need this. Okay, so this is 0, and this one will be 3, this one will be 5. Okay, since out of these 6 quadratic residues, no pair other than 0 plus 0 add up to become multiple of 11, we can say that a squared and b squared are both congruent to 0 mod 11, and hence both a squared and b squared are multiples of 11. And then we are done with this. So you can write your QED, or you could draw your little black square, okay? And as such, using quadratic residues, it's a very short answer, but I believe we have solved the problem. Of course, if you are an Olympiad teacher and then you think my solution is not clear enough, you could write down in the comments. And then if you guys have any other solutions to this other than quadratic residues, you guys can also write it down in the comments. I would like to hear you guys' feedback. Okay, so this is the video for today, and then in the next video we'll be talking about a problem that junior and senior IMONST 2 have. Okay, so it's like an overlap again now. So that's the video for today. We'll see you guys in the next video, and ciao ciao.